So we're going to look at some more curve sketching here and using the first and second derivatives, but remember the variety of things that we look for here. We can look at for intercepts, we can look for asymptotes, we can look at end behavior. We wouldn't necessarily have something for every single one of these every time, but this is kind of a nice checklist we could go through mentally to see what we need to find here, okay? So let's start out here. We're looking at this quartic equation, x to the fourth minus 12x cubed plus 48x squared minus 64x. And let's start with the kind of pre-calculus things first, and then we'll address the parts that are going to require some calculus, okay? So, what do you see? We'll let you guys kind of take this in whatever order you happen to see it in.
The domain is all real numbers.
Good, okay. The domain of a polynomial function is going to be all real numbers. Alright, so x is any real number. Okay? What else do you see? Good, yeah, there's no constant at the end, so the y-intercept is actually 0, 0. Anything else?
What's the end behavior? Is it like both go up?
Yeah, the end behavior, is it going up on one end and down on the other, or vice versa, or are they both going up or both going down? Yeah, they're both going to go up on this one here, okay? So the end behavior is it's going to go like this on the left and this on the right. I don't know what's going to happen in the middle, but I know what's going to happen on the ends. And by the way, because I already see that, there's something else I know I won't have here. Yeah, I'm not going to have any horizontal asymptotes, and because of my domain, I know I'm not going to have any vertical asymptotes. Okay, so this one actually is going to be not too bad. Okay. So, let's start by sketching what we know to be true so far. Okay? I know I have a y-intercept at 0, 0. And I know that there are no asymptotes. I know the end behavior is going to look like this. Alright? You may not want to draw it yet, just because we don't know quite where it connects, but I know that's going to happen at some point. So let's do the last thing that's not going to take any more calculus, and that is our x-intercepts. Okay? And this one actually gave us a little hint. We could factor to find our x-intercepts. That's kind of nice. Alright? So, x-intercepts, 0 equals, how are we gonna factor?
Grouping.
Okay, we could factor by grouping. Okay. Can we do something before we even group it?
Take x out.
Yeah, let's take out the x. And then we've got an x cubed minus 12x squared plus 48x minus 64. Okay? And now let's try grouping this here, okay? What do you think?
X to the third and 64, because 64 is 4 to the third. Right?
It is, yeah. X cubed minus 64, because that's 4 to the third. And then we'll put the minus 12x squared plus 48x. together. That's really good. Okay, so that means that the x minus 64, I could take out an x minus 4, and what's going to be left over here?
X squared minus.
Same, opposite, always positive, so the sign here is going to be
Negative.
plus.
Plus.
It's same in the binomial, opposite here, so it's plus 4x, always positive, so it's plus 16. By the way, guys, sum and difference of cubes shows up a lot in AP Calculus, okay? So if you struggle factoring that, you need to review it a bit, okay? That's why we throw a lot of these examples that have it in there. Alright, so then the second group, what are we going to take out? A negative 12x. Okay, negative 12x, and then in parentheses we've got an x minus 4. Okay?
Wait, isn't it plus 4? Oh no, I'm sorry.
And now we've got x times x minus 4 times x squared plus 4x plus 16 minus 12x. So it's going to be x squared minus 8x plus 16. Which it,
What did you just do?
I just took out, we had the common factor of x minus 4. So I took that out. And then I combined what was left over. Okay? So what's x squared minus 8x plus 16 factor into?
X minus 4.
Yeah, x minus 4 squared. So we actually now have x times x minus 4 to the third power. So what are our zeros here, guys? 0 and 4. So the x-intercepts are 0, 0, and 4, 0. So 1, 2, 3, 4. There we go. Now, because that 4 has a multiplicity of 3, what are you probably going to see here? It's going to cross over, but it's going to kind of level out, right? Aha, that's a plateau point, which is also going to be a point of inflection. Okay? Back in pre-calculus, we saw where it leveled out, but we never really knew what was going on there, right? And now we can see what's going on there. We have a plateau point and a point of inflection. Okay? So, now we need to go through our first derivative. F prime of x is 4x cubed minus 36x squared plus 96x minus 64. Okay? And now we just need to figure out what the zeros of that are. Okay? And now, guys, here's a little tip. If you see a case where, okay, when we were getting our zeros, we saw that triple root. And we know it's going to level off there, then we know probably x minus 4 is one of our factors, right? So I could kind of anticipate that this is going to factor into x minus 4 times something. And to figure out the something, what can I use?
Synthetic.
Yeah, synthetic division, alright? So, 4, negative 36, 96, and negative 64. And I'm going to divide it by an x minus 4. So I put a little 4 in the box. 4, 16, negative 20, negative 80. 16 times 4 is 64. Add down and I get 0. So I know it's x minus 4 times 4x squared minus 20x plus 16.
How do you know that you can take an x minus 4 out?
I know I could take an x minus 4 out, or at least I think I can take an x minus 4 out, because this had a multiplicity of 3. And remembering what I learned in the past about polynomial functions, when that 0 had a multiplicity, it went up and it leveled off, and then it went through the x-axis. And now that I'm in calculus, I realize that must have been a plateau point.
I'm not getting it. I mean, the multiplicity of 3 is 4x plus 3.
You remember how, just sketching this is how we would have sketched this last year. We would have seen the multiplicity of 3, and we wouldn't have drawn it going straight through 4. We would have drawn it kind of leveling off, going through 4, and then increasing. Okay? Now that I'm in calculus and I've seen the concept of a plateau point, and I know what a point of inflection is, I'm now anticipating, I'm kind of using, this is where the synthesis of what you've learned in the past and what you're learning now kind of comes together with. I'm kind of anticipating that this would work. Now, you could try it and it may not work. I know this one does work because I ended up with a 0 at the end, so it came out evenly. Okay? So that was kind of nice. If you don't, you can always just try other things. You could try factoring by grouping. It'll work here. I'm just trying to show you an alternative idea. Okay? Now, I also see there's a 4 that those things have in common, so I'm going to pull that out. And I've got an x squared minus 5x plus 4. And then I notice, hey, that x squared minus 5x plus 4 factors. And I have an x minus 4, so now I have two x minus 4s, and an x minus 1. Okay? So what are my critical numbers here? X equals 4 and 1, right? So we're gonna test that. Okay. Now before we test that, let's go ahead and find our second derivative and see what we can do with that, okay? So f double prime of x, we've got a 12x squared minus 72x plus 96. I'm going to divide everything by 12. Okay, so that's 12 times x squared minus 6x plus 8. And that factors into x minus 4 times x minus 2. Okay, so the possible points of inflection are at x equals 4 and 2.
What about the 0?
What about the 0?
I mean, if you said it, the function equals to 0, isn't it there's a 12 there? So
Well, if I set it equal to 0, 12 times 0 would be 0, so
Yeah, why is it not an inflection point? Wouldn't it be
12?
zero?
You'd have to have a, oh, why is 0? Oh, because you don't have a 12. It's not like there's a 12x out here. It's just a 12.
Oh,
Okay? Alright, so now let's look at the different possibilities here, okay? You'll notice here we saw that the critical numbers were at 1. Let me color code it here. We're at 1 and 4. And I had a possible point of inflection at 2 and 4. Okay? Now in the next example, I use the number lines. If you prefer that, you're welcome to do that. If you like using a table like this, you could do that as well. But notice I have now 4 different intervals that this has been divided up into. Okay?
Can I ask a question?
Yes.
Why do we say possible points of inflection?
Because remember, the second derivative has to change signs for it to actually be a point of inflection. That's a great question. Okay. Alright, so let's see. The critical numbers are where the first derivative equaled 0. So I'm going to put that in here. And the possible points of inflection are where the second derivative is equaled 0. Okay? So let's work this out here. Okay, we've got from negative infinity to 1. What's going on with our first derivative? F prime of x. So if I plug in 0 to my first derivative, what do I get? Positive or negative? Come on, guys. Stay with me here.
negative.
It's negative. We got a negative 64 at the end. So if I plug in 0, we get a negative. Okay. What does that tell us?
Just f of x is decreasing.
F of x is decreasing. Okay. So f is decreasing.
Jason, why didn't we put like a mark where 1 was? Why did we have 0 on the graph?
I haven't really graphed anything since I put what I thought we had with the zeros. That graph you see up there is kind of the graph we would have come up with in pre-calculus.
Okay.
Because that doesn't take into account any of our derivatives yet. So that's kind of what we think it's going to look like. So now we're just getting more detailed view of it. Okay. So now we have the interval. Well, let's check our second derivative. In this interval, if I plug in 0 to our second derivative, what do I get?
You get positive and
I get a positive. Okay? I get a positive. So there's for our second derivative, f double prime of x. Okay? So that means f is also concave up. Now, here's the thing. The intervals for concavity are different than the intervals for increasing and decreasing, right? So this positive is going to continue all the way until we get to 0. Or until we get to where x equals 2. Alright? So I know I'm concave up on the interval from negative infinity up to 2. Okay? Does that make sense?
Because the derivative, the second derivative of 2 is 0, right?
Correct. So everything to the left of that or below that is going to be the same concavity. Alright? That's why I just filled those in without even checking them, because I know this is kind of why I personally prefer using the number lines instead of a table like this. I'll have a separate number line for the first derivative and for the second derivative. Okay, but I show you both just so that you can make your own decision. Now I do need to test my first derivative between 1 and 2. So if I plug in 1.5 in my first derivative, 1.5 minus 4 is negative, squared is going to be positive. And 1.5 minus 1 is positive, so I have a positive times a positive times a positive. So I know that f prime is positive, which means f is increasing. Okay? And now that I can see that, what do I know about the point where x is 1? It's a min point because I went from decreasing to increasing. So I have a minimum at 1. And now if I plug that in, I get 49 minus 86. It's going to be negative 37. Okay, so this min point is at 1, negative 37, I know now. Okay? Now I can test the rest of this, okay? By the way, notice that I know it's going to continue to increase until I get all the way over here to where x is 4. Okay? Because again, the intervals for the first derivative are different than the intervals for the second derivative. Okay? But I do need to check my concavity between 2 and 4. So if I plug in 3 into my second derivative, I have 12 times 3 minus 4 is negative, times 3 minus 2 is positive. So positive makes a negative. So that means that my function is concave down. Okay, so second derivative, negative, negative, okay, so concave down, and that's for the interval from 2 to 4. This was concave up on the interval from negative infinity up to 2. Okay? Okay? So now we just have our last thing here, okay? And that is we need to check the interval from 4 to infinity. We need to check the first and second derivatives. So if I plug in 5 to my first derivative, what do I get? Positive or negative? Positive. All right? So that means my function is increasing. So let me ask you, what does that mean about where x is 4? Do I have a max or min point? Yeah, I have a plateau point. There's no change in direction. Okay? So there's a plateau at 4, 0. Okay? Now, is that a point of inflection? Well, let's check our second derivative. If I plug 5 into our second derivative, 12 times 5 minus 4 times 5 minus 2, is that positive or negative? 12 times 5 minus 4 times 5 minus 2. Positive, okay? Positive times positive times positive. So this is positive. which means now I'm concave up. So is 4, 0 a point of inflection?
Yes.
Yes. Okay? So that is a point of inflection. Okay? So, this sketch that we had before is a pretty good sketch, but now we know a little bit more about what's going on. We know right there not only is the tangent horizontal, but also we are changing concavity there at 4, 0. Here the tangent's horizontal at 1, -37. Okay? So there's a more detailed graph than what we were able to do before. Okay? And there's a little picture of it. Okay? Oh, we missed one of our other points of inflection. I overlooked it. Right here, where it's 0, we changed from concave up to concave down, right? So that's our other point of inflection. And that's at the point 2, if you plug 2 into the original function, you have 16 minus 96, so that's a -80, plus 196, so that's 116 minus 128, so 116 minus 128 is a -12. Alright, so 2 -12 and 4, 0 are points of inflection. Okay? Alright, any questions, comments?
Does it say right there that 4y is a plateau? Is that what it says, or 4, 0?
4, 0 is a plateau. So the plateau is the point of inflection. Alright, so let's analyze and sketch the graph of cosine over 1 plus sine. So let's just start with kind of the easy stuff. Where are the x-intercepts going to be?
Y equals 0.
When y is 0, so what's going to make that function 0?
Pi over 2.
Okay, pi over 2,
And 3 pi over 2.
3 pi over 2, and then if I keep adding 2 pi to each of those, and that's because those are the points where where cosine equals 0, right?
What about where sine of x equals -1?
Okay, what are those going to give us?
Undefined
Asymptotes, yeah, those are going to give us asymptotes. So, and those are going to be vertical asymptotes where sine x equals -1, so that's when x equals what? Hmm?
No.
No, 3 pi over
3
2.
pi over 2.
3 pi over 2,
How do you know if the asymptotes are?
and that's it. Well, horizontal, remember, we're looking at as x approaches infinity, what's happening to our function.
Approaches and
Now, something interesting happened right here. Notice one of my x-intercepts was also what I thought was a vertical asymptote. So what actually occurs at 3 pi over 2?
hole.
I have a hole, okay? I have a hole. So this is actually not an x-intercept. Well, I should say this.
Of the limit.
Yeah, it's not an asymptote, it's not an x-intercept, there's going to be a hole at 3 pi over 2. Now, does anyone have a good way where we could find the y-coordinate of this?
Just plug it in.
Well, if I plug it in, I get 0 over 0, right?
Oh, derivative of the top over derivative of the bottom.
Yeah, L'Hopital's rule. L'Hopital's rule. If I plug that into the derivative over the derivative, which would be a negative sine x over cosine,
Negative 10x.
well, negative sine of x is a negative negative 1, right? So that's going to be 1 over, what's cosine of 3 pi over 2? 0, uh-oh, okay. So that's no good.
That's not good.
So let's try, why don't we try L'Hopital's rule again? What's the derivative of negative sine?
Negative cosine.
Negative cosine. And the derivative of cosine is negative sine. So now when I plug in 3 pi over 2, and I'm doing that because I'm trying to take the limit as we approach 3 pi over 2 so I can figure out where this hole is.
0 over
I get 0 over negative 1, which does equal 0. So we found it as an x-intercept, but it's actually not an x-intercept. Notice we just proved that on the x-axis there is going to be a hole. And actually not just at 3 pi over 2, but at 3 pi over 2 plus 2 pi plus 2 more pi plus 2 more pi, because this is a periodic function. Alright, does that make sense?
So in the test, should you make like n pi over 2 or something like that?
Oh, like do a plus
A rule
2
that-
pi n or
Yeah.
something like that?
Rule that applies for every number.
You could. When you sketch it, you are obviously just going to sketch part of this, but so here's what we've got so far with our sketch. We're going to have here's pi over 2, pi, 3 pi over 2, 2 pi, and then 1, 2, 3, 4. So there's like 3 pi over 2 plus another 2 pi is going to be here. So I know there's going to be holes here and 1, 2, 3. And also here. That's going to be a negative pi over 2. Okay, 3 pi over 2 plus 2 pi is going to be 7 pi over 2. So I've got these holes here. Okay? I also know that I'm going to have x-intercepts at pi over 2. So that's there, and then every 2 pi from there. So 1, 2, there as well. Okay, if I keep going here one more spot, there will be another 0 there. Okay? This is making sense?
Yeah.
Okay. What about a y-intercept?
X equals 0.
Okay, so what do I get when I plug in x equals 0?
1 over 1.
1 over 1. So yeah, I've got the point 0, 1 here. Okay, so that's kind of nice. So let's plug that in. There's a point. Okay. We already kind of talked about the domain restriction. X cannot be 3 pi over 2 plus 2 pi n, where n is an integer. Okay. Is there a horizontal asymptote here?
How do we find the horizontal asymptote for this?
Well, think about as x continues to go towards infinity, what's going to happen to our cosine and our sine?
They're gonna oscillate.
They're going to oscillate, right?
What do we mean by oscillate?
just go back and forth between the same two values.
Yeah.
So our function's going to do the same thing,
Yeah.
okay? So that means no horizontal asymptotes, okay?
Many critical numbers.
What's our period going to be?
What do you mean, what's our period gonna be?
How often is this going to repeat?
Oh, okay.
It's going to be 2 pi.
How do you know it's gonna be 2 pi?
What was 2 pi?
Well, because we're dealing with sine and cosine, and notice here it's still cosine of x and sine of x.
You're divided one by another.
So both of those have a period of 2 pi, so it's going to repeat every 2 pi. Okay?
Sure, dividing these out, how should you know that the period will continue? I remember from last year.
If there were a coefficient in front of the x, like if it were a cosine of 2x and sine of 2x, then the period would be 2 pi divided by 2.
It's inside.
Yeah, if it's inside the trig function. So now there are some where you're just not gonna be able to tell. Like if it was cosine of x squared or something, you know, you wouldn't really talk about the period because you can't just look at it and tell. Okay. Same thing here, like symmetry. I don't know if there's any symmetry there or not without further analysis. Okay, so. We wouldn't necessarily look at that. But now we have critical numbers that we need to find. Okay, so for that we're going to have to do first derivative. Points of inflection, so there we're going to have to look at the second derivative. We'd have to work through all of that. Okay? So now we're going to take the first derivative. We need to use the quotient rule. So f prime, let's change colors here. F prime of x is going to be a negative sine x times 1 plus sine x minus cosine x times cosine x all over 1 plus sine x squared. Okay. So now we have a negative sine x minus sine squared x minus cosine squared x over 1 plus sine x squared. And I'm going to factor out a negative 1 from here, and that makes it 1. So now I have a negative sine minus 1 over a 1 plus sine x. Alright, so now if I'm finding my critical numbers, those are going to be when sine is a positive 1 on the numerator. That would make it equal to 0. Okay, when sine x equals 1, which that's going to be when x is pi over 2 plus 2 pi n. Or it's also going to be undefined when sine is negative 1. Okay, and for space I'm going to put plus or minus here. Or it's at negative 1 at 3 pi over 2 plus 2 pi n. And we actually already have that those are holes from what we've done with the domain restriction. So now we will look at that when it comes to increasing and decreasing. But those are not, we know for a fact already they're not going to give us critical values. So let's go with pi over 2 and 3 pi over 2. Let's go one more. So pi over 2 plus 2 pi is going to be 5 pi over 2. And that's going to be 7 pi over 2. And f prime, let's see, if I plug in 0, f prime is going to be negative 1 over 1, so that's going to be negative, which means my function is decreasing. If I plug in something between pi over 2 and 3 pi over 2, I'll plug in pi. That's going to be a negative 0 minus 1 over 1 plus 0. So again, that's going to be negative 1 over 1, so that's negative. So it's again decreasing. So what you can see happening here is I actually am going to have a plateau point at pi over 2. Okay. Then if I plug in something between 3 pi over 2 and 5 pi over 2, I'll plug in 2 pi, and that's going to be negative 1 over 1, so that's negative. Okay. And then, let's see here. Plug in something between 5 pi over 2 and 7 pi over 2, which would be 3 pi. Sine of 3 pi is 0. So it's again negative 1 over 1. So that's going to be decreasing. So my function here is going to be constantly decreasing. Now that makes us rethink a little bit about what we were doing earlier. Earlier we had said that it looked as though there were holes at every multiple of 3 pi over 2. And now we're seeing that this function is constantly decreasing, which obviously is not possible if we have holes there. In fact, we're seeing that there are not any relative max or min points, that all of these points are plateau points. So that means we've got to rethink things here. So this, where sine is 1, we must have been correct originally in stating that there was actually going to be vertical asymptotes when x is 3 pi over 2 plus 2 pi n. So all of these actually are going to be asymptotes. Okay? Not holes. And this is just kind of the stuff that you got to work out as you're trying to sketch this. This is why we kind of sketch as we go, but definitely want to work in pencil because we might realize more information here as we go along. Okay. So now, because this is decreasing, now we have these horizontal asymptotes, we actually can see what our function is going to look like a little bit better because we're going to have these plateau points and then we're going to hit the asymptote. So it almost looks like kind of a variation of your tangent or cotangent graph. Okay, so it's going to just repeat like that. So that's all dealing there with our second derivative. We were able to tell that. Now let's see if working with our first derivative. Sorry, let's see if working with our second derivative. Adds any more information to the situation. Okay, so let's do this. Take our second derivative. So f double prime of x is going to be, again, the quotient rule. So we're going to have to use Oop, I lost a square back here. That wouldn't affect any of our signs because those are all positive anyways. It wouldn't affect any of our work, in fact, because that would still be 0 when sine was -1, and those would still be positive when we were figuring out our sine diagram, so that all still works. Okay. So now, second derivative. We have a negative cosine x times a 1 plus sine of x squared minus a negative, so this is going to be plus sine x plus 1. I just kind of factored out the -1 from the numerator to make that a plus, times the derivative of the bottom. So this is going to be 2 times 1 plus sine x to the first times cosine x, the derivative of the inside. Alright, so now what I'm going to do is I'm going to actually factor, and you can see here, all over a 1 plus sine x squared. Alright, so now I'm going to factor. You'll notice here I have a cosine, and also both parts have a 1 plus sine x squared if I put these two together. Alright, so I'm going to take out a cosine x times a 1 plus sine x squared. And that means I'm going to have a -1 left on the first part, and all I'm going to have left on the second part is actually a 2. So this whole thing is just -1 plus 2, which means that's what this simplifies to. It's just cosine over 1 plus sine x squared. And this whole thing is over 1 plus sine x squared squared, so that's the 4th power. Now this is kind of cool because now I can cancel that out with that, and there's only 2 left. And now I have cosine x over 1 plus sine x squared. Okay? So now, possible points of inflection. Where are those going to occur? Those are going to occur when either the second derivative equals 0, which would be when cosine is 0, which takes place when x is pi over 2, 3 pi over 2, and so on. Okay? Both of those plus 2 pi n. Or when sine squared is a -1. Or not sine squared. When sine is -1. And we already stated above that sine is -1 at 3 pi over 2 plus 2 pi n. So we already have that accounted for right here. Okay? So you notice here, those are our points of inflection. So I can actually use the same sine diagram down here. I'll just extend this and have my second derivative. Okay? So let's plug in the same kind of values here. If I plug in a 0 into the second derivative, I get 1 over 1, which is positive, which means my function is concave up. If I plug in, let's say pi, cosine is -1, and that's going to be 1 plus 0 in the denominator, so that's going to be a negative, so now I'm concave down. Alright, so that just showed that at pi over 2, this point right here, pi over 2, 0, that is a point of inflection. Okay? And then also, if I tried between 3 pi over 2 and 5 pi over 2, that's at 2 pi. okay, we're gonna see that it is positive, and that makes it concave up. And then if I plugged in 3 pi, we would be back to negative. You can test that out on your own if you want. Notice I'm going to be concave down. So you'll notice here we have another point of inflection, this time at 5 pi over 2, 0. So those x-intercepts are actually the points of inflection. All right? So the points of inflection are at pi over 2 plus 2 pi n, 0. Okay? So that's the graph of that one. There's a lot to it, but if you're just careful and go through it one step at a time, it's not too bad. Now, let me just show you one thing. Those of you who really love the trig and are a little bit more savvy problem solvers might be able to recognize this as an opportunity. What if I took this original function and I decided I was going to multiply this by 1 minus sine x over 1 minus sine x. Now, you'll notice what happens here is I have a cosine times 1 minus sine x over a 1 minus sine squared. Well, 1 minus sine squared is cosine squared. And now I have a 1 minus sine x over cosine. I say, well, how in the world does that help us? Well, it might help you if you're trying to take the derivatives. If you wanted, you could then split it into 1 over cosine, which happens to be secant, minus sine over cosine, which happens to be tangent. So then when I was going to find my first derivative, I could just take the derivative of secant, which is secant times tangent, and minus the derivative of tangent, which is secant squared, and I could find it that way. Now, you may say, well, then finding the zeros when I'm dealing with secants and tangent is harder than when I'm finding it with cosines and sines. And you may be right. So this is a possibility. I'm not necessarily saying that this is recommended, but just be aware that you can do things like this in this situation. Okay?